Hello everybody, this is Suvarchala, working as an associate professor in the Department of Computer Science and Engineering. In this video, I would like to explain about disjoint sets, a new data structure which is useful for various applications of graph related problems, most of them. So, and also what are the operations we can perform with this special kind of data structure. So, I'll discuss about disjoint sets and operations, detecting cycle, graphical representation, array representation, as well as weighted union and collapse find rule, various operations of the disjoint data structure. So what is disjoint set? The term itself indicates that disjoint means no common. So this disjoint data set data structure is a data structure that keeps track of a set of elements partitioned into number of disjoint. Disjoint means non-overlapping subsets. The main operations on this data structure are union and find. So that's why this disjoint set data structure is also known as or popularly called as union-find data structure also. So what is union? What is find? That means union means whom union, find means what we are supposed to find. This union-find algorithm is an algorithm which performs three useful operations on this data structure. Those three useful operations are union, find, make a set. That make a set is going to be performed, that is creating a new disjoint data structure with this union and as well as find operations actually. This disjoint set is going to be used in various applications actually. First we'll discuss what is a disjoint set. Let us assume that S1, S2 are the two sets, then they are disjoint if intersection of S1, S2 is null. It's a common disjointness property of a set theory actually. For example, when we are considering two graph components represented by two sets of vertices and edges, let us assume that all of us aware of that, what is a graph, what is a set of vertices, what are the set of edges and how to represent graph internally. All these were discussed in previous video. Now, let us assume that S1 is ABCD, S2 is HI. So, S1 is ABCD is one graph and S2 is HI is another graph. Initially, we will assume that this is one graph and this is another graph. Two graphs are there. And S1 is the set of vertices of graph 1, S2 is the set of vertices of graph 2. Let us add an edge. For example, these two are going to be joined by adding an edge. Let us assume that we are adding an edge BH. So this is the edge we would like to add. So when we would like to add this BH, then this S1 and S2 must be union. That means it becomes a single graph, no? So when we are adding by adding an edge, these two graphs are union, that is the graphs are going to be combined and they become a single graph only. Then what are the vertices of this graph? A, B, C, D and HI also. That means union of these S1, S2 will be the set of vertices of this new graph actually. This is a common thing. But remember, when we are like to do this union operation, that means when we would like to add an edge, for example, we would like to add an edge BH. When we would like to add an edge BH, any edge, that source vertex and destination vertices, both source and destination vertices must belong to two different sets. Source and destination vertices must belong to two different sets actually. In this example, B belongs to first graph, that is S1, and our H belongs to S2, that is set of second vertices actually. then only we can add as an edge to that graph. So that what happens, no cycles are formed. If these two vertices belongs to two different sets, then adding an edge means union of these two sets doesn't give any common vertex. So that's why, for example, when we are using this new edge and union of S1, S2, we will get an S3, A, B, C, D and a HA. This is value. For example, we'll consider further. Let us assume that I would like to add an edge DI. So we would like to add DI means here, D is from here to here. This is the new edge we supposed to add, DI. When we would like to DI in S3, DI means here, for example, now newly formed graph is having ABCD as well as IH. This is the S3 is the new graph set of vertices. When we would like to add DI to that particular edge, to that particular graph, then D and I both belongs to same set, that is S3. If both belongs to S3, we supposed to add this to my graph. You observe here, by adding this edge, what happens? A cycle formed. A cycle formed. That means both vertices D and I, any edge we would like to add, both vertices are belonging to the same set. By adding an edge, they, in that particular graph, a cycle forms. So that's why detection of cycle is easy by using this disjoint sets actually. As earlier I specified, various applications are there. Check the network connectivity. We will discuss that in the next video related to the components, by connected components and connected components of a graph. In that we would like to check connectivity of the graph. That is, articulation point will be identified through this particular set of disjoint sets only. This is one of the application which is real-timely. In real-time applications, network connectivity checking can be considered. Find the least common ancestor and also to form a minimum cost spanning tree. That too by using Kruskal's algorithm. In Kruskal's algorithm, when we would like to generate a minimum cost spanning tree, then it will take, it will check formation of the cycle every time. So this formation of cycle just now we discussed, no? So by using this concept and disjoint set concepts, easily identifiable, we can identify a cycle is going to be formed or not in the Kruskal's algorithm. And equivalence relations and many more are there actually. So this is a new data structure. Disjoint sets is a new data structure, specifically having instead of normal operations, which are the operations generally we will perform on any data structure: traversal, searching, sorting, adding an element, deleting an element, and so on and so forth. But in this particular, a new data structure, disjoint sets data structure, union and find are the base, with make a set operations are the base operations. And these are having a specific applications in our computer science. So, for example, when we are representing set as a tree, let us assume that. So, how to represent these disjoint sets and how to perform these operations. The operations on disjoint sets are going to be performed based upon the representation of this set as in the form of a tree also. We can represent as a set in the form of set form or in the form of a tree also. For example, if you are representing set as a tree, let us assume that 2, 4, 5, 9, 11, 13, 30. These are the set elements. With this set of elements, we can form a number of trees actually. So, multiple trees are going to be formed by using this set of elements. For example, I have given various ways. For example, this is one kind of tree, second, 3, third. Like that, we can form various representations of this because there is no any particular specific rule to form a tree in this example. So that's why set can be represented as in any tree. So how these operations are going to be performed? Let us assume that we are maintaining the collection, a disjoint set data structure S as S1, S2, etc. up to Sk. These are all considered as a disjoint dynamic sets. Each set is identified by the representative. So how can you represent a set? Various techniques are there in this representation of this set. Because normally we will give a set name, but when we are representing disjoint set, generally one of the members of the set is going to be the representative of the set. One of the any member can be considered as the name of the set itself. But to simplify the process of representation, generally we will consider when it represented as a tree, the root value is going to be considered as the name of the set. So for example, when we are considering the previous example, if we are representing this disjoint set in the form of a tree, this can be represented with 13. The name of this tree is 13. This is 4. This is 5. That means we can use any of these numbers. But when we are representing in the form of a tree, we will consider generally the root is the name of that particular set. So each set is identified by a representative, which is some member of the set in general. But most of the time we will consider if it is represented in the form of a tree, the root value will be considered as a name of the set. So in some applications, it doesn't matter which member is used as a representative, but only we have to consider the representative of a set twice without modifying the set between the request. So anything can be considered, but we have to keep in our mind the representative of a set modification. When we would like to modify the representative of a set, then we have to properly observe what are the consequences. So whenever we are requesting for any of the value or any for representative of a set, if we get the same answer twice, both times, then we can consider it as a representative. This is some application. In some applications, there is no any specific thing to which member is going to be used as a representative, but we have to take care of that. If any accessibility when we are going to do the same operation twice, then our same process twice, if we are going to get the same answer, then we can consider it as a representative. But in some other applications, there is some rules are going to be followed, which one of them is going to be representative. In some applications, the smallest value of the set is going to be representative. Or in some applications, the largest value can be considered as a representative. So please understand, representative is nothing but it's named like that actually. As I told you, if the set is going to be represented as a tree form, then root can be considered as a representative of the set. So that's why each element of the set is represented by an object and it is going to be considered as a single-turn set. So the various operations we can perform with our disjoint sets are make a set, union and find set. We'll discuss one by one in detail. The terms are itself indicates that make a set means creates a new set with only one member as X. So a new set is going to be created with only one single turn set is there. So that is going to be represented. And if X is already, for example, if the particular set is having some elements, it creates a new set with only member is X. If X is representative of the set, let us assume that if it is already there in our set, then it will be added to the set if it doesn't exist, because disjointness is no, repetition is not allowed. So make a set is a operation used to create a new set by adding an element if it with the existing set also, if it doesn't exist in the existing set. Union of X5. In this example, in this operation, union means here X is one set, Y is another set. X is a representative of one set, Y is a representative of another set. That means it unites the dynamic sets Sx and Sy that contains both S and X and Y values. But when we are using this disjoint pair, here we are going to assume that this Sx and Sy are disjoint sets. Then only union is going to be performed. That means the assumption of Sx and Sy are assumed to be disjoint before this operation is going to be considered. The new representative is because Sx can be added to Sy or Sy can be added to Sx while doing this union operation. So what will be the representative? Representative may be either X or Y or any some member of the Sx or Sy. Anything can be representative. Please understand, representative means it is representing, means it's a name, just like identifier we are giving, no? So S is equal to 1, 2, 3. S is the name of the set. So that name can be any one of the members of the set. That is representative. Usually when representative of either Sx or Sy is chosen as a new representative, because already existing subsets are available, no? So that's why generally we used to avoid the confusion. A new set is formed means a new representative is going to be chosen by us. Whenever we are performing this union operation of Sx and Sy, once a new set was generated, the original sets are going to be get destroyed, removed. That means it has to be removed from the collection because this is already written in a new set, no? So that's why the original sets must be get destroyed or removed. Those are not going to be considered further. A new set is going to be considered further. We have to remember this point when we are going to discuss about our set operations in a proper manner actually. And third one is find set. Find set returns the pointer to the representative of the unique set containing X. Find means searching. So if that particular X is available in any of the set, the respective representative is returned. In other words, you can say the name of the set is going to be returned where this particular X exists. When we are considering this running times of these two operations, make a set, union and find operations, then N is the number of elements to be added to the any set, disjoint set, and N will be the complexity, and M is the total number of make a set, union and find operations. So we'll discuss further about these operations. So that's why these sets can be represented as in the form of a trees, as I explained previously. But remember how we are representing these trees. It's not a normal tree. This union and find structures are going to be represented by trees with parent pointers. Please observe. With parent pointers. Parent pointers means here, generally how will you represent our tree? From parent to child, the path will be there. Even though we didn't perform or we didn't put any arrow mark in normal tree structure, so root to children, any parent to children, the path point will be considered. But in case of disjoint structure, disjoint sets, if you represent in the form of a directed trees, that means trees generally we won't give any direction. Directed, undirected are related to graphs only. Right now? But for trees generally we will undirected only, but the traversal is generally from the root to the children. Reverse direction is also possible, but we won't consider it as a reverse direction. But you observe here, in the form of a directed trees, if you observe these two trees, how these trees are represented from each node, pointing is going to be to its parent, towards the parent. So, the root of the tree is called as a representative of the tree. As I told you earlier, representative can be anything. But when we are representing in the form of a directed trees, the root of the tree is going to be representative of the tree. So now in the first case, what is my disjoint set tree? This is 33 and this is 7. The names of these disjoint set trees are 33 is the first one, 7, which are roots. And please observe how the arrow marks are going to be pointed towards its parent. Towards its parent. We can't perform this all operations of normal trees with these special trees. These trees are only to represent our disjoint set data structure. We can perform only union and find operations. Of course, a refined form of these two operations are going to be performed by us. So, these are also known as up trees. Because we are directing upward direction now, so that's why we will, sometimes these trees are also termed as up trees. So, up trees notes the point to the parent, not the children. Only one pointer per node will be there, not multiple. One pointer per node. That means from a node to only its parent. This disjoint set union-find, each disjoint set is its own up tree. Each set is one separate tree. And the root of the tree is the name of the disjoint set. That is the representative of the disjoint set. If you are having this, hope you clear how the tree is represented. So the tree is represented in the form of a tree. We will call it as a directed tree, and the directions are in upward direction. That is up trees. In this, each tree, root node value will be considered as the name of the tree. And are representative of the tree. We can perform these find and union operations also. For example, union of ij. Ij is the tree with root as a I, j with as a root of the another tree. In other words, ij are the two disjoint sets. Two roots of two different trees. Remember, I is not equal to j. Both of them should not be equal. The unite the trees make one tree as a subtree. One tree is going to be subtree of other. What is meant by union? Union means we are writing all unique values. But remember, when the disjoint sets are represented in the form of up trees, then we will add one of the trees as a subtree to the other tree. Union of ij means ith tree can be a subtree of j, or j can be a subtree of I. Either of them is okay. I'll give an example here. For example, let us assume that I have 7 different sets. That is set 1. 2 is another set. 3 is another set. Like that, each element is one set individually. Let us assume that initially I have 7 disjoint sets are there. And I want to make a single set. Or some other. So, if you would like to perform this union operation, initially each set is represented by 1 tree. That means 1 tree means only root nodes are available to us. 1, 2, 3, 4, 5, 6, 7. That means 7 trees are there for us. 7 disjoint sets are there. 7 trees are there. We will do union. For example, let us assume that the first one is union of 1, 4. Second one is union of, let us assume that 7, 5. Okay, third one is union of 2, 6. Then I will perform union of 7, 2. Various unions I can perform. For example, first union of 1, 4. 1, 4 means the tree 1 and the tree 4 must be unioned. What is meant by union here? Add one of the trees as a subtree to other. I am adding 4 as a subtree to 1. Of course, this is also correct. I can add 1 as a subtree to 4. This is also possible. Both of them are valid. Both of them are valid. 1 can be subtree of 4 or 4 can be subtree of 1. Now 7, 5. 7, 5 means 5 is subtree of 7. Pointing towards subtree, no, towards 7. 7 is a parent. Next to 2, 6. 2 is a parent and 6 is a subtree of 2. This is another one. Then 7, 2. 7, 2 means these two must be union. We are adding this 2, 6 as one of the subtrees of 7. So that's why we can perform any of these a sequence of union operations will give us the process. Whenever we are doing union, the initial are going to be destroyed or removed. When I am using 1, 4 is removed. So when I am using 2, 6, individual are not available. Then when I am using 5, 7, 5, 7 is not available. 3 is a single set. That means when we are using this union operation, whenever this union operation is performed on 2 subtrees, the individual subtrees are going to be supposed to be removed by us actually. This is the way we will perform this union operation. While doing this union operation, we are getting now doubt. In what way this is going to be added as a subtree? As we discussed earlier, so if you are union 2 subtrees, one of them can be subtree of the other tree actually. When we are using union of 2 trees, one of the tree can be subtree of another tree. Is there any specific rule? So there is no any specific rule, but we can form a rule according to our convenience also. For example, in this example, union of xy, assuming x and y are the roots of the 2 subtrees, and now you observe, so union of 1, 7 means 1 is going to be considered 1 is a subtree of 7. Let us assume that we are going to get like this 1 and 1 is having its children. Entire tree is going to be subtree. One child of our 7 now. Or this can be done other way also. The 7 can be added as a subtree of 1 also. No problem. That's why to make it more clear, these union approaches can be done by using 2 techniques. One is union by height, another one is union by weight. Union by height or union by weight. Actually, we can do either of them, no problem to us in general. But to follow some specific rule so that we can perform in a proper manner, so these unions may be performed by using any of these 2 approaches. That is union of weight or union of height. These 2 approaches can be used by us actually. What is union of height? So if you observe here, union of height means make the tree with the smaller height a subtree of the other. This can be done. So for finding a height of a tree is not a big issue for us. So that's why if you are aware of the height of the tree, then the smaller height of the tree will become a subtree of the larger height of the tree. So that we have some specific technique to follow this actually. So in such cases, make a tree with a smaller height subtree of other tree. If this is the case, in the previous example, what is the height of the first tree? Height of the first tree is, for example, if I am including root also 1, then it is 2. Then 1, 2, 3, this is 3. 2 is lesser than 3, so this will become a child of this. Of course, if you follow that approach, there is no any mandate requirement of following that approach. It depends upon our application. You can follow such a way so that a common process is going to be adopted by us. So in this example, when we are considering this example, if you observe this 13, what is the height here? 4. 1, 2, 3, 4. Height of this tree is 4. And the height of this tree is 7 trees. So you will be having 1, 2, 3. So what is the least height? This is the least height. So this becomes a subtree of 13. So we are adding a pointer to, you observe here. We are adding a pointer to 13 means union of 7, 13 is just we are making the 7 tree as a subtree of 13. Why? Because 13 tree is having height 4 and 7 tree is having height 3. So lesser height tree is added as a child to the larger height tree. This is one way. Another one way is union by weight. So union by weight means a tree with fewer number of elements becomes subtree of the. Instead of calculating height, we are going to use weight. Weight means number of terms you can consider. Number of nodes in other way. So less number of nodes tree is become a subtree of the tree having more number of trees. If this is the example 7 and 13, 7 tree. 7 tree, how many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes are there. So this is the weight of the, number of nodes is the weight. Number of the nodes is the weight of the tree here. So what is here? Weight 1, 2, 3, 4, 5, 6, 7, 8. So in this case, 13 trees having weight as 8. So this is the weight of the tree is 8. Here weight of the tree is 10. So this is lesser one. So this you observe, this 13 tree becomes a child of 7 tree. That means here when we are performing a union, so in brief, union operation is used to make or merge two disjoint sets which are represented in the form of a tree. Let us assume that. Each tree is going to be represented by its root. When we would like to do union operation on two trees, the representative of one tree should not be equal to the representative of the other tree. So in such cases, the first tree can be a subtree of the second one, or second tree can be a subtree of the first one. Either of them is okay. But to follow a proper approach, we can use union in two techniques. One is union by height, another one is union by weight. First, to find the height of the subtrees, first subtree, second subtree. Whichever is the find the height of the first tree and second tree. We would like to union these two trees, but remember it's not normal trees. It is up trees represented for a particular disjoint sets. Union of these two trees, the lesser height tree is added as a subtree to the tree which is having a more height. Same in the case of weighted approach also. What is weight? Weight is the number of nodes of the tree. So less number of nodes trees will be a subtree of the tree which is having more trees. So you can follow normal union, you can follow union by height, or we can follow union by weight or any other technique also depending upon our application. But the key concept is adding union of two disjoint set trees means adding one of them as a subtree or a child of the other tree. That's all. So when we are doing this operation, the constant time. Just we are adding it's a child, no constant time operation. Find operation. Find I means to identify the set that contains the element I. So various disjoint sets are available. Collection of disjoint sets are available to us. We will find where this particular I exists. The respective root is going to be returned. That is respective representative will be returned as a answer. That means in which tree it exists. So in which tree it exists means the respective tree name. Start at the node and represent the elements I and climb up the tree until the root exists. So first we have to, in case of find operation, it will take a little bit time. First we have to check each, terminal nodes first. So start at the node and represent the element I and climb up with until the root is reached. Return the element in the root representative. So the time complexity is we are passing or traversing maximum height of the tree. So that's why order of H will be the log. That is the height of the tree will be the time taken to find. For example, when we are using here find 13 means 13 we have to find 13 up to find 9 means 9. Where is 9? We have to check 9. From 9 towards upward direction we have to move so that we can find. So find 14 means wherever 14 is there, from 14 onwards, you have to find in which tree it exists. That means find operation, it will give the representative of the tree or root of the tree in which it exists. That's all. So for example, when we are considering this find operation, follow X to the root and return the root, the name of the disjoint set. So in this example, find 1. Find 1 means we are starting from the lowest value, we are moving towards 1. So 1 is the 1. Root is 1. Find 3. Where 3 exists? 3 here. 3, there are no further movement. 3 itself is the root. Find 3 is 3. For example, find 4. Where is 4? 4 is here. Moving towards upward direction. So automatically 4 is parent of 4. I mean root of the tree in which 4 exists is 1. Find 6. 6 is there. We will move towards upward direction till there is no further traversal. That means till we reach the root. From root there is no upward direction traversal, no. So that's why there 7 is the last value. So that 7 is the parent of the node, parent of the tree or representative of the tree or name of the tree in which the 6 exists. So union, assuming ij are the roots, pointing I to root, union of 1, 7. Just now I explained you, same here, 1, 7. So 1 can be added as a child to the 7 or 7 can be added as a child. What if I or j is not in the root? For example, if there is no, first we have to check union, always we are considering I and j are in roots of the trees. Then if I and j are not in the root, what happens? As I told you, union of 1, 7. Let us assume that we may consider union of 1, 6. 6 is not a root of any tree in these 3. Collection of trees are 1, 3, 7. Collection of trees are 1, 3, 7. 3 trees are there. 1 is there, but 6 is not there in this collection. What I supposed to do? If it doesn't exist in the tree, we have to use a find algorithm and find the root of the tree. So this union of 1, 6 will become union of 1, 7. Because 6 doesn't exist as a root of any of these 3, then what we supposed to do? I have to find 6. Find 6 must be done. Find 6 means from 6 to, it will go upward direction. It returns 7. So 7 is the root. So union of 1, 6 becomes 7. Union of 1, 7. Because 6 is the element which exists in the tree 7. So that can be formed. So that's why run the find on I or j first and use the return values for joining or for performing union. Why do we join roots and not just the nodes? Why we are doing this? Why? Because when we are adding the nodes, then once we are performing, what is the initial status we consider? Once we are performing union, the original sets or original uptrees must be destroyed or removed. But when we are joining directly with the, without having any root, for example, I would like to join 1 as well as 6 means I cannot destroy completely 6 here because 6 is not a root, no. So that's why I cannot destroy the entire tree 7. If we destroy, what happens? So other elements are going to be vanished. So that's why when we are performing union, we are going to take only roots only, but not the normal nodes. Why? Because after union, the original values has to be destroyed to avoid the repetition of the data. Because it's a disjoint set, no? So that is one of the reasons. So it is going to be easily implemented. For example, when we are using, you can implement by using array notation, or we can represent either using it or tree representation. So this is array representation. If you observe here, so let us assume that we are having 1, 2, 3, 4. Once again, it's better to implement a tree using an array than with the nodes as an objects. Instead of representing, each tree can be represented either by using a list representation or node object representation or array representation. It's better represent as a tree generally. If you are representing a tree as a single dimensional array, So when we are using the single dimensional array, how to represent it actually? A different approach has to be performed by us. Right? So initially, up of 0 is considered as an empty or number of disjoint sets. Using array with node objects as elements actually. Let us assume that we are using an array up having 7. Of course, it may be because here we are having 7 elements, we have taken as a size of the array is up array is 7. So, size of the up array is 7, starting indexing value is 1 to 7. So, up of 1, up of 2, up of 3, etc. etc. So, how to represent the content of the each element? So, up of x is equal to I means the node x is the parent node of I. Node x is the parent node of I. Right? Because observe here, the values and indices are same. If the values and indices are different, then we have to take different approach. So what is here? 1. 1 is the root here. Is any parent for the root? No. So that's why you observe 0. So for any element, the respective value is 0 means it's a root. It's a tree. It's a representative of the tree. 2. 2's parent is 7. So 7 is represented. Okay. 3. 3 don't have any root. So that's why 0. It is a root, no parent to 0. 4. 4. Parent of 4 is 1. We are representing. That means the array values represents its parent. It's a parent nodes. If the no parent means if it is a root, then the parent value is 0 we are considering. You observe here 5. 5 parent is 7. 7 represented. Okay, 6. 6 parent is 2. 2. 7. 7 parent, no parent because being a root it is 0. So how many zeros are there? Here 1, 2, 3 means 3 individual up trees are available. 3 disjoint sets are there for us. Right? So like that we can simple implementation can be considered when we would like to implement them, these disjoint sets by using trees means by using a single dimensional array we can use. Of course, it has its own advantages and disadvantages. So advantages, accessing easy, parent accessing is very easy for us. Disadvantage, how to represent if the values are not same as our indices actually. We have to take another dimensional value. When we are using this union operation, a sequence of unions, various kinds of trees are going to be generated as we discussed in earlier slides. There is no any specific rule. So that's why, for example, I am having this value, disjoint sets initially as a 1, 2, 3, 4, etc. and disjoint sets are there. I am using this union operation as a sequence of unions will give or makes a single disjoint set can be represented actually. When we are doing these operations, for example, I am using, you observe in this example, union of 1, 2, 1 is added as a child to 2, union of 2, 3, this 2 is added as a child to 3, and the union of 4 and so on and so forth. Just we are doing the addition of the second left side to the right side. When we are doing the same process, you observe what kind of trees I am going to get. What kind of trees? These trees are known as skew trees. Once skew trees are generated, find operation will take more time because the height of the tree is going to be more, no? So, in such cases, if you don't have any proper rule for union, it may be generating skewed trees also, which is a bad case actually. To avoid that only, we can use either union by height or union by weight. So, that means if we are having such type of union operations, randomly if you are going to add, sometimes possibility of generation of a skew trees. So, because of this skew tree, what happens? It's a bad case, literally speaking. Why? Because it takes more time find, because you have to start from your last value towards the root value to find the root of the tree. So that's why find takes more time. That's why to avoid that, as we discussed earlier, follow some rule. Okay, by union by height or union by weight can be considered by us. Using array-based uptrees, the cost of the union of ij and find of x. Cost of union of ij is a constant 1. Why? Because one tree is added as a subtree. Only one pointer is going to be updated. I and j are roots. Otherwise, it depends. If both are I and j are roots, its cost is only 1. Otherwise, it depends upon the find. Why? Because if ij are not roots, we have to find out the roots of the respective nodes, no? So, find algorithm must be used. So, it depends upon the cost of the find. Coming to the find of the cost of the find algorithm. So, worst case, it is order of n. Previous slide, we have seen skew tree. In case of skew tree, then order of n worst case. And this is the one of the worst cases, skew trees. Right? So, best case can be order of 1 also sometimes. So, what is the total number of union operation to reach the last tree will be, if there are 1 to n are there. So, total number of union operations are going to be having n union operations we have to perform to form a tree also. So, initially this one, 1, 2. Then how many? We are having n minus 1 trees, n minus 2 trees, and so on and so forth. To form a single tree, n unions must be performed by us. So, the total number of union operations to reach the last tree is n minus 1 operations, and the time complexity is the order of n minus 1, that is order of n. A single union operation is order of 1, but to form a complete tree of nodes n, then that means complete tree of having n disjoint sets to a single disjoint set union operation, order of n. N unions, no, n order of n will be the time complexity. The uptrees are going to be sometimes may become too tall, as we discussed earlier. That is, a skewed form is there. In order to make this disjoint union and find operations must be performed very effectively. As we earlier we have seen that find operation may take worst case order of n, and the union of n disjoint trees into a single tree, it will also take n times it has to be performed. No? So, to improve our performance of these two operations, both union and find algorithms, two operations, some with restrictions we are going to consider. That is, union is known as weighted union, and path is finding path. Find algorithm will use path compression technique. That means these two algorithms improve the union as well as find algorithms, the base algorithms of union and find algorithm. Both of these will get to, for find is average case is going to be height of the tree, that is order of log n, and amortized is going to be order of 1. Amortized complexity means one operation individually. So, weighted union. What is weighted union? Instead of arbitrarily joining two roots, always point the smaller tree to the root of the larger tree. As we discussed earlier, it may be smaller tree means number of nodes, or it may be height of the node. So, each uptree has a weight, the number of nodes. The idea is to limit the height of the tree of the uptree. Trees with more nodes tend to be deeper. So, that's why we can use union by rank or a height or a similar ideas, but more complicated to implement actually. As earlier I explained you, weighted union, a special cases of union by height and union by weight. Those will come under this weighted union. So, that's why we will join two roots depending upon their height or depending upon their weight. Weight means number of nodes, height means the level of the uptree actually. And trees with more nodes may tend to deeper one. So, we can use union by rank also can be considered. So, for example, if you are considering 2, 1, 4, here we are using here, what is the number of nodes are 2, number of nodes are 1, here number of nodes are 4. That is weight. So, when we would like to union them, first 2, 4 means this 2 less no, that is added as a child to the 7. Because 2, 4 when you are doing this union, union of 2, 4 can be considered as a child. Then we are going to add union, then 1 is going to be less number, 1 is added as a child. So like that we can add so that it happens the less number of node trees as a subtree of the more number of trees. To these, when we are adding this representation of the respective arrays is also we have to be considered. Because in case of normal union, no problem to us. But in these cases, every time calculating weight is going to be very difficult for us. So that's why we will represent the respective weights also in a parallel subarray. So up is an array having its parent values. Weight is the respective roots. Wherever zeros are there, the respective roots are going to be considered as the roots of the tree or representatives of the tree, and we will put the respective weights also. Whenever a tree is generated, respective weight is going to be considered. Right? So we can just use an additional array to store the weights. So for 1 tree, 2 is the, and for 3 tree, 1, and for 7 tree, it is 4. You please observe wherever the roots are there, for them only respective weights are represented. So when we are using this, or we use negative numbers also to represent the roots and their weights. Instead of using 2 arrays, we can use 1. So what we are using previously, we are using as a 0. 0 represents the respective node is a root actually. But instead of that, we will represent with weight. To distinguish whether it is a parent number or a weight, we will represent with a negative sign. So here, 1 is a root. Previously it is 0. But what is the weight of the this particular subtree? It is a 2. So that's why we are representing it with a -2. Here 3. 3 is a tree. Name of the tree or root it is. So only one node is there. Weight of the tree is 1. So we are representing it as a -1 now. Previously it is 0 if you observe. Third tree is a 7 tree. 7 tree means in the place of 7 we are having 0. 0 by representing 0 as its parent is no parent, no 0. But now we are representing them its weight. What is weight of the 7 tree? 4. So number of nodes are 4. Instead of representing 4, we will represent. That means negative value indicates it's a weight and the respective node is a root. Positive value indicates it's a parent of the respective. So that order of n space is going to be saved by us. Of course, space is not a critical in certain issues, but to save the space, this can be done by us. And weighted union performance is going to be, because it is representing the height, no? So that's why order of log n will be the find algorithm, and the union rule prevents the linear up trees. That is, skew trees are going to be prevented because of this weighted union. That's why it always promises order of n is 1 is the omitted complexity I as well as weighted union. So average case is going to be still order of log n, but in case of find algorithm. So when we are using this optimized disjoint set union-Find, and in 1984 proved that M weighted union and find with the path of compression operations on the set of n elements of the worst case as well as the average cases as height of the tree 1. Since find operation has now the find operation we didn't refine it. Weight union operation was improvised by using weighted union concept actually. So find operation has to be performed by us. How to perform this find operation? As we discussed earlier, the find operation will take order of n, linear complexity. So it has to traverse to the depth of the tree to find the complexity, cannot be changed with the weighted union. So with weighted union, it cannot be changed. So we have to improvise our find algorithm also by introducing the parent address with each node along with its weight also. That means our tree consists of now 3 parallel arrays. The first one is the node numbers. Second one is the parent node, or -1 if it itself is a parent. It is a parent means -1. Weight number of nodes in that particular tree with a negative sign. So we will use this collapse find algorithm. By using collapse rule, we can reduce it, the height of the tree. That means the weighting rule for find union of the sets and collapsing rule, and simulate the behavior of the weighted union on various sequence of the elements. So when we are using this parent of I means it will give minus count of I, -1 less than or equal to 1, I less than or equal to 8. Then we can perform actually. So various algorithms are going to be used by us. So we can use our weighted rule and union rule and collapse find rule, and we can solve this problem as an exercise. So these are the algorithms. So make a set algorithm is make a set int of v, a individual element, no? So parent of v is v itself. And find algorithm, find is if v is equal to parent of v, return v, else find set parent. Recursively we are calling. And weighted union, we are checking first find algorithms. If it is not equal to b, then only both are doesn't belongs to the same tree only. We are using this parent of b is equal to a or. This is a simple algorithms. So this we implemented without considering any of the efficiency part actually. So algorithm find set, n worst case, 1 best case, union sets, n square worst case, n best case. But by using weighted and collapse find rule, it will be improvised. So these are the algorithms for make a set. We have to update parent as well as the size of the V also. How many elements are there in that particular rooted up tree can be considered. So set of size of V is 1. Coming to the union of the sets, we are finding the parent of A, parent of B. If A, B are not roots or representatives, both are not equal, then only we are going to union them. So size of A is less than size of B, and we are swapping them A, B, so that you can use any other logic also. Parent of B is equal to added parent of A can be parent of B is going to be A. That means lesser size is added as a child to them. Then we have to enhance the size also, no? So size of A is equal to size of A plus size of B. Similarly, find when we are using, if find means it's a parent, we are returning. Otherwise, we are parent of the find set parent is going to be returned. So we are reducing. That means we are modifying our rules, union as well as the find operations, so that the complexity of these two operations are going to be properly manageable by us. In both worst case also, it can be similar to the average case. So that's why we are going to use this weighted union and collapse find rules whenever we would like to use the disjoint sets as one of the data structures in our applications, so that the efficiency of these operations are going to be enhanced. We will use in the next this disjoint sets concept in bi-connected components as well as connected components of the graphs with finding the articulation points also. So that is network connectivity checking can be done by using this disjoint set data structure that we will discuss in the next video. So in the next video, we'll discuss about this disjoint sets as well as implementation of these disjoint sets for finding network connectivity, that is articulation points, to find the articulation point as well as bi-connected and connected components concepts. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.